In this lesson, we're going to talk about L'Hopital's rule to find the value of limits that are undetermined. We met in the past some limits that were undetermined. For example, the limit when x goes to 1 of x squared minus x over x squared minus 1. This limit is undetermined. If you were to evaluate the value of x into the fraction, you would get 1 minus 1, 0 in the numerator, and 1 minus 1, 0 in the denominator. So technically this limit is a 0 over 0 kind of limit. Now we cannot divide by 0, so this is what means to have an indetermination. So in the case of this limit, what we used to do was we would find some way that we can actually modify this expression, and the tool that we used back then was factorization. So if I factorize common factor in the top and a square difference in the bottom, I get that I can cancel x minus 1, and my limit is simplified as x over x plus 1, which is an expression that I can evaluate when x is equal to 1. The numerator would be 1 and the denominator would be 2. There is an alternative way to do these kinds of limits, and that is L'Hopital's rule. Especially, L'Hopital's rule is very useful when we have functions that cannot be factorized. For example, the limit when x goes to 1 of ln x over x minus 1. If we evaluate this limit, we're going to see that the numerator at 1 is going to be 0, and the denominator is going to be 0. So again, this is a 0 over 0 kind of limit, and we cannot factorize it. There's nothing we can do with this. So L'Hopital's rule is going to help us do these kinds of limits in a very easy and simple way. L'Hopital's rule is defined for functions that are fractions, and we are going to use L'Hopital's rule when we have one of these two cases. The first case is going to be that the limit of the numerator and denominator are both 0, so we get the case of 0 over 0 like the two examples from before, or the limit of both the numerator and denominator go towards plus or minus infinity. In those cases, we're going to get an indetermination of the form infinity over infinity. If we have these two cases, then L'Hopital's rule says that the limit when x goes to a of my original function f over g is going to be equal to the limit when x goes to a of the derivative of f over the derivative of g. Unfortunately, the proof of L'Hopital's rule requires the Cauchy's mean value theorem, and that is outside the scope of the syllabus for mathematics, analysis, and approaches HL. But what we can do is we can give a very soft proof of L'Hopital's rule for a particular case. Let f of x and g of x and a value a in the real numbers such that f of a is equal to g of a, and that's going to be 0. Additionally, the derivatives of f and g at that value of a exist, and in particular g dash of a is different from 0. So we're going to assume these conditions to give a very soft proof of L'Hopital's rule. And again, because of these conditions are required, this proof is not valid for every function. It's only valid for functions that have a value of 0 at a. Now with this in mind, let's consider the limit when x goes to a of f of x over g of x. Then, because f of a and g of a are 0, I can say that this is equal to the limit when x goes to a of f of x minus f of a over g of x minus g of a. And if I divide top and bottom by x minus a, then the limit becomes limit when x goes to a of f of x minus f of a over x minus a over g of x minus g of a over x minus a. And this is the definition of the derivative of f. So this is limit when x goes to a of derivative of f, and the denominator is the definition of the derivative of g. So this would be over derivative of g. This concludes the very short proof of the soft version of L'Hopital's rule.